Okay, so now what I want to do is I want to discuss some of the theorems that we've learned. Okay, and I actually mentioned in the last time I was going to start with the fundamental theorem of line integrals, but I'm not going to start with the fundamental theorem. I'm not going to start with the fundamental theorem of line integrals. I'm going to start with the fundamental theorem of calculus. So what does the fundamental theorem of calculus say? So let me remind you. It says if I want to integrate from x equals a to b of a function, or the derivative of a function, f prime of x, sorry, let me make my x a little bit better. F prime of x dx. Okay, this is equal to f evaluated at b minus f evaluated at a. And what I want to do is I want, clearly the left-hand side is an integral because there's an integral side. But what I want to point out is that we can actually interpret the right-hand side as a certain type of integral. So this is also an integral. And I'm going to put this in quotes, even though it doesn't need to be in quotes. Okay, I can actually define to you precisely why we should call this an integral, but for now we're going to call this an integral. And notice it's f of b minus f of a. So direction here somehow matters. Remember, if I do the order of integration differently, if I go from b to a and do that order of integration, I'm not going to get the same thing as if I do the integral from a to b. So remember, by definition, if I go from b to a, that's going to be minus what I do when I go from a to b. Now, what does that sound like to you? Does that sound more like the integral of a scalar field or a vector field? If you try to put it into the context of our class, it sounds more like the integral of a vector field, because vector field, if you switch the order in which the parameterization goes, you multiply the integral by minus 1. And so over here we have f of b minus f of a. Okay, so this is just the fundamental theorem of calculus. Okay, now let's compare this with some of the theorems we've learned so far. So remember, the fundamental theorem of line integrals says the following. The fundamental theorem of line integrals says the following. So again, if I have a curve going from, let's say this is r of a. So the starting point is r of a, and the ending point is r of b. Okay, then what it says is the following. It says the integral on the curve C of the gradient of a scalar field. So remember, this is a vector field. If little f is a scalar field, its gradient is a vector field. And then I dot this with the tangent vector. This is equal to f of r of b minus f of r of a. And so again, we can kind of compare these two things. I have the derivative, ds, dx, these two things go, because remember, the important thing when we're doing the line integral of a vector field is that this has direction. And dx has direction. It goes from the left to the right. We don't talk about it in Calc 1 so much, but it does have a direction. It goes from the left to the right, at least in this interpretation, because if we change the order of integration and go from b to a, we multiply this by minus 1. Just like if we change the order of integration to go from here to here, we multiply things by minus 1. So this is the fundamental theorem of line integrals. Derivative inside an integral on the left-hand side. On the right-hand side, again, we can kind of think about this as being an integral. We can think about this and this as being an integral over a one-dimensional object, that is a curve. and this we can think about being an integral over a zero-dimensional object, that is points. Okay, so now let's look at the next theorem that we learned. Let's look at the next theorem that we learned, which was Green's theorem. And so Green's theorem says if we have some region D, so D is going to be a region in the plane. If we have some region D in the plane, and we have the so I'm going to write it a little bit differently. I'm going to just, well, you'll see. It's slightly different than what you see in the book, but only in the order that I'm writing. And I have some function q, and I do the x derivative of q minus the y derivative of p dA. I can think about this in two different ways. I'm going to think about it in the following way, though. Actually, let me change the colors here so I can keep my color scheme consistent. So you're going to have the x derivative of q minus the y derivative of p dA. Is equal to the line integral. Okay, so what does the line integral be? It's going to be the line integral around the boundary of D with the counterclockwise orientation. So I'm going to put the boundary of D here. So partial D means boundary. I'm going to put a circle there and an arrow, meaning we're going in the counterclockwise orientation of the vector field PQ dotted with dr. Oh, sorry. Once again, let me change colors to make the color scheme consistent. So the vector field PQ dotted with dr. And if I have a parameterization for r, if my parameterization for r is given by x of u, y of u, something like that, we can also think about this as being the line integral of the scalar field p dx. I'm really not wanting to change colors. P dx plus q dy. But again, we're doing an integral on the left-hand side. We have derivatives on the left-hand side. Okay, so we can kind of think about this as being like a derivative on the left-hand side. We're integrating a two-dimensional object. And on the right-hand side, we're integrating a one-dimensional object that doesn't have the derivatives. Okay, and again, the order matters. So here I do f of b minus f of a. There's an orientation on the 2 points, a and b, f of b minus f of a. Over here, there's an orientation on the boundary. I have to do this line integral around the boundary in the correct direction for Green's theorem. Okay, so this is Green's theorem. Okay, the next thing that we learned, we just learned that very recently, is Stokes' theorem. And Stokes' theorem says if we're integrating over a surface, the curl of a vector field. Okay, so again, this is going to be, this is a line, surface integral of a vector field. Once again, I don't know why I'm not doing my colors well. Curl F dotted with the normal vector. So I'm doing the surface integral of the curl of F. This is going to be equal to the line integral around the boundary of my surface, and we're going to be integrating F dotted with dr. Now, what you can actually show is that Green's theorem, you can derive Green's theorem from Stokes' theorem. So this is Green's theorem. this is Green's theorem, and this over here is Stokes' theorem. Sorry, I guess it goes right here. That's Stokes' theorem. How can you derive Green's theorem from Stokes' theorem? Well, up here, you can just think about the vector field F that's equal to P, Q, 0. And if you compute the curl of F, you're exactly going to get this right here. So this is actually equal to the curl of F. Okay, so this is Stokes' theorem. And again, on the left-hand side, what do we have? We have the curl of F. This is a derivative, right? The curl of F involves derivative. So this is like a derivative. Again, it matches up over here. And on the right-hand side, and it's a two-dimensional integral. We're integrating over a two-dimensional object. And over here, this is a one-dimensional object, and we don't have the derivative there, you see. Okay, so we're doing the line integral of a vector field over here. Okay, and the interpretation for both of these things, like what is actually going on here, well, if we have, like, what is this saying? If we have a surface like this, okay, I'm going to draw it as a surface kind of in R2, or sorry, in R3. But the same reasoning holds if we have a surface in R2, it's just going to be part of, a subset of R2. Well, the curl kind of represents the extent to which the vector field is flowing in the counterclockwise direction. So if you have all of these things right here, and I did this in class as well. And so what's going to happen, if you think about the flow right here, the flow in this cell going in that direction is basically going to be canceled by the flow going in that direction. So if you add up all of the flows, the only flows that we're going to be left with are the flows going around the boundary here. And so adding up all the flows corresponds to this part of the integral, and then just looking at the flows, adding up the flows going around the boundary, those are kind of the tangential flows, and that's what we have here. Okay, so this is why we might expect something like Stokes' theorem or Green's theorem to be true. Okay, now the next theorem that we're going to look at, we haven't covered this in class yet, but this is the divergence theorem. So remember, divergence says the divergence of a vector field. So let's imagine F represents velocity of a fluid flow or something like that. The divergence of a vector field tells us how much a vector field is spreading out. Okay, positive divergence at a point means that at that point the vector field is sort of spreading out. Negative means it's coming into that point. Okay, so imagine I have a surface in R3 that encloses some volume. I have a surface that encloses some volume, and I want to know how much is flowing, like what is the net flow of velocity through this surface? Well, the conservation laws, conservation of mass, should show there should be some connection between the flow through the boundary and the total flow. So if I have flow inside, if I have flow in the interior of that volume, flow to the left is going to cancel with flow to the right. So the only net flow over the whole volume is going to be the flow going through the boundaries. Okay, and that's exactly what the divergence theorem says. So now I'm going to do a triple integral over a volume. Okay, so it's a triple integral over a volume. We haven't talked too much about integrals over volumes yet. I mean, we've done triple integrals, but we're going to do a triple integral over a volume of the divergence of a vector field. Okay, so remember, divergence of a vector field is a scalar field. So this is a scalar field. So this is just an ordinary triple integral that we've seen before. So this dA, this is going to be equal to the surface integral of my vector field F dotted with ds. Okay, and again, why am I dotting it with ds? Well, again, the fluid is flowing through the boundaries. If I'm thinking about F as being the velocity field for a fluid, it's flowing through the boundaries. And so the part of the velocity vector that's flowing through the boundaries is going to be the portion of the vector that is parallel to the normal vector to the boundary. because the part of the velocity flow that is parallel to the boundary is not going to cause fluid to flow through the boundary. It's just going to cause it to sort of skirt along the top of the boundary. So this is the divergence theorem. Okay, and again, I've got the derivative on the left-hand side doing a three-dimensional integral, and on the right-hand side, I have a two-dimensional integral, which is one dimension less than this, and I'm integrating without the derivative. And notice in all of these, including in the fundamental theorem of calculus, there is an orientation that matters here. Okay, there's one last thing that I want to point out. So when we're doing things like curl, stuff like, if we talk about curl, so curl is kind of a concept that only makes sense for a three-dimensional integral. But divergence makes sense for any dimensional integral. So there's actually also a two-dimension version of the divergence theorem as well, which I'm going to write over here. The two-dimensional version of the divergence theorem says that if you want to do an integral over a two-dimensional version of the divergence theorem, basically it just says if you want to do a line integral, you have an integral, a region D in R2 of the divergence of F dotted with ds, not dotted, times dA. This is equal to the line integral on the boundary of the domain, and again, it has an orientation, counterclockwise orientation, of F dotted within, which is the outward pointing normal vector to the surface. So again, this is a line integral of a scalar field ds. Sorry, I guess in this formulation the orientation doesn't matter. Okay. And so we get something like this. And so again, this is going to represent like the amount, again, if F is a velocity vector field, this is going to represent the amount of fluid flowing through the boundaries. And that's just going to be equal to the divergence taken over the whole region here. Okay, so this is called the divergence theorem. This is sort of a two-dimensional version of the divergence theorem. Okay, so that's all that I want to say in this video. Again, I know there's a lot of stuff going on, but the point of this video and the one I made before is not to be like, once you see this video, now you understand everything. But I did just want to give all of the different types of integrals and theorems in one spot, so you can it might be easier for you to see the connection between all of these things. And how it kind of really just is, they are all just multidimensional versions of the fundamental theorem of calculus. So I hope this helps. If not, sorry you wasted 20 minutes, 30 minutes of your life watching it.